So, audio check. My voice is clear, loud and clear to everyone. Yes, guys. Let me quickly share my screen. So, the screen is also visible. Awesome. Perfect. So, today we will be doing time series forecasting. But before we start anything new, let me know if there are any questions. And also, we don't have any all the learners online yet, so we can wait and we can talk about if there are any questions or anything. Yes, guys. Not specifically me, but it could be either me or someone from the team. Is the content in self-learning same or different? You mean to say the content we are doing? Self-learning is basically a kind of self-preparation before we start, before we do the live sessions. So something is there in self-learning, and most of the things we do in live sessions. Yes. Anyone? Yes, guys. Any questions? Book for Python and data science. The one we have shared. I think that's for machine learning and everything. Yeah, that's for machine learning and everything. Yes. Okay. So I think we can start now, guys. So today's topic will be time series forecasting. Perfect. So before we talk about the time series forecasting or anything, let's understand what is time series data, right? Yes, guys. What is time series data? Anyone? Changes according to the time in a particular intervals, right? Changes data content with reference to time. Yes, when time is the main factor to evaluate. See, time series data is that's all answers are mostly correct. The time series data is any data that is time indexed, right, with respect to time. When we have some information that is with respect to the time, for example, daily temperature, or the stocks, or anything, any information that is with respect to the time, that is called a time series data, right? Understood what is the time series data, everyone? Perfect. Now, there are few prerequisites about time series forecasting when it comes to the time series data. So first, data should be time series. We need to have time series data. Okay. And second, it should be in equal intervals, right? It should be in equal intervals. Clear? Equal intervals. Equal intervals mean if we have hourly temperature, we need to have hourly temperature only, right? If we are working on some stock, price of some specific asset, and if we are working on day trade, so we need to have the information daily. So the time tick should be equal, it should be uniform. We cannot have unequal intervals, like we have the temperature for current hour, then we have for next 2 hours, then next third hour, the next second hour, and so on. Like, we cannot have this data. If there is a data like this, we cannot implement the time series forecasting. Time series forecasting can only be implemented on the data with the equal intervals. Got it? Right? Perfect. So apart from equal intervals, time series data, there is one factor called stationarity, right? There is a one factor called stationarity. Now, what exactly is stationarity here? Do we know what exactly the stationary word means? Anyone? Fixed, static, that do not change, right? No movement. Exactly. Exactly. So let me explain the stationarity with some figures. Okay. So ideally, the time series data is somewhat like this, right? That's how a time series data looks like. Some y, and here it is, the time. Oops, sorry. That's the time, and the other one is time. This is y, and this is time. Okay. So this is how time series data looks like. Now, if we see the value, the y is actually having some relation with respect to the time, right? There is some sort of relationship of the series y with respect to the time, right? So we can say this this line or this time series data, this time series is actually some function of time, right? Make sense? Let me write it clearly. We can say that this time series data, this specific time series, what we have, this series is having some relationship with respect to the time. Y equals to function of time. There is some relationship with respect to the time. The time can explain some sort of trend in the series, right? So that means that this series is a function of time. Yes? Or if the series is not the function of time, its moving average is going to be the function of time, right? Right? There could be a possibility, suppose if the series exactly is not a function of time, but that its moving average is going to have some relation with respect to the time. So that means it's a non-stationary series. Yes? This is a non-stationary series, right? Sure. See, we were talking about the stationarity, and stationarity means if the time series is having some relation with time or not. If time can explain some sort of trend in the series, then it means that series, the time series, is some function of time. Yes? Right? And this kind of data, this kind of series is called non-stationary series. What is it? It is non-stationary series. That's an example of non-stationary series. Okay? Clear? Now let me plot another example. Okay, it will be clear. Don't worry, it will be clear. Because it's moving. It is, okay, I'll show you the stationary, then it will be clear why it's not stationary. See. So let's suppose I have in another series, and that's how that series looks like. Okay, suppose this is how another series looks like. Now, if you see, this do not have any function with respect to the time. The time cannot explain anything in the value of y, right? Yes? The time cannot explain anything in the values of y. Yes? In this series, in this specific trend, the time has no relationship with the y. It's almost parallel, means there is no relation, no explanation, right? Yes? So this is called stationary because there is no change. This is called stationary. Okay? Clear? Stationary means no relationship. Non-stationary means some relationship. Right? Stationary means no relationship. The series is independent of time. The series is independent of time. A non-stationary means it has some relationship. Right? Non-stationary means there is some movement, and that movement can be explained by the time. That movement can be explained by some function with respect to the time, right? Yes, y is some xyz factor. Just like why is the actual time series what we are talking about here? Why is the time series what we are talking about here? Now let's understand what is the difference in non-stationary and stationary. We understood both the figures, right guys? Everyone understood the figures? Okay. Now why we are calling it not stationary? Because there is some movement with respect to the time, right? There is some movement with respect to the time, and that movement can be explained by some function y equals to a function of time ft, right? Right? Yes guys, everyone, does this make sense? Why it is called non-stationary? And the another figure, second, it is stationary because there is no movement with respect to the time. It's moving definitely, but time cannot explain the movement, right? Time cannot explain the movement in y. Yes, the series y in figure 2 is independent of time, right? We'll talk about what like what time series data is, whether it is stationary or not, and what we want. As of now, what exactly is stationarity? Is it clear, everyone? What exactly is stationarity? Is it clear, everyone? Perfect. Now let's come to this point. A time series data, a real time series data, or a practical time series data, whatever we can take as an example, the weather, the stocks, crypto, anything. If there is something time series, it's not possible to have a stationary time series data, right? Right? Not practically possible. But now there is a strange fact, right? We know that uh, practically it's not possible. Practically it's not possible to have a time series data stationary. But again, there is a strange fact that the time series algorithm can only work on a stationary data, right? The time series algorithm can only work on a stationary data. But practically, stationary time series data is not possible. Yes? So we understood that what first we understood what is stationarity, right? First we understood what is stationarity. Now we also discussed that a time series data cannot be stationary, right? A practical time series data cannot be stationary. And then there is a strange fact that all the time series algorithms, or what algorithms we will be discussing today, that is Arima, can only work on a stationary data. Yes? Yes? Understood? The Arima can only work on a stationary data. You understood what is stationary and non-stationary? Is it clear what is stationary and non-stationary? Yes. Okay. Now, the algorithm what we will be doing can only make the forecasting on a stationary data. It cannot work on a non-stationary data. Okay. Is this clear? Right? Perfect. Now, how can we do this thing? Yes, it's not practically possible. So, how we can do this thing? Yes, we transform the data. Then where we use the algorithm, we are going to discuss that thing, guys. Just small discussion more, and we will understand how exactly we are going to do this. Yes, we transform the data. Practically, we cannot have a stationary time series data, but the algorithm can only work on a stationary time series data. So we take a non-stationary time series data and we transform it to a stationary time series data. Right? Again, practically we cannot have a stationary time series data. We can only have a non-stationary time series data, but the algorithms we use can only work on a stationary time series data. So we pick non-stationary time series data and transform them to stationary time series data. Yes. Make sense? What is the logic? Logic about? It's like converting files to the software. Yes, kind of similar. Yes, guys. Please let me know if there are any questions. The logic, the concept of stationarity is clear, everyone? What is the motto for modeling what we predict? We are actually trying to do time series forecasting, right? Yes, time series forecasting. And what do we understand by the forecasting? Yes, guys, what do we understand by forecasting? Exactly. So that is our objective. That is our objective. Clear? Easy? Perfect. Again, to brief out the stationarity concept, we understood what is stationarity. The series, if the time series are not exactly the time series, if the moving average of a time series is some function of time, then it's not a stationary series. Means the movement in the value can be explained by the time. If the movements in the time series data in the values of y can be explained by the time, it's not a stationary series because there is a movement, right? But if there is no movement, or the movement whatever we have in y cannot be explained by the time, the movement in y cannot be explained by time, that's called a stationary data, that's called a stationary time series data. Clear? Now, practically, a stationary time series data is not possible. We cannot have a stationary time series data. We can pick any practical example, stocks, weather, temperature, anything. We cannot have a stationary time series data, right? We always be having a non-stationary time series data. So how we are going to like why do we need to learn about the stationarity? Because the algorithms what we have right here in order to make the forecasting, they can only work on a stationary data. They cannot work on non-stationary data. So what we actually do, we do some statistical transformation techniques to transform a non-stationary series to a stationary series, and then we implement the algorithm on a stationary series, and then we retransform them to their original scale. Understood the stationarity concept, everyone? Easy? Awesome. Awesome. Perfect. Apart from the stationarity, there is one more thing called seasonality. There is one more thing called seasonality. Now let's understand what is seasonality. So if there is certain pattern that is getting repeated on a given interval of time, that's called seasonality. Okay? If there is some pattern that is getting repeated after some time period, that's called the seasonality. So we can see there is a pattern that is getting repeated here. So this is called a seasonality. This is called the seasonality in the data. And again, another strange fact, we should not have seasonality to implement the forecasting algorithm. Okay? We should not have the seasonality to implement the forecasting algorithm. Clear? So, stationarity we want, seasonality we don't want to implement the forecasting algorithms. Got it? Stationarity is something we want to have in the data, but seasonality is something we don't want to have in the data. Something like null values, sorry, no, it's not null values, it's some sort of repetition, some trend what we have, some, certain repetition what we have in the data. Yes. We need to drop the seasonality also, and again there are statistical measures to treat the seasonality also. See why we need to drop them. If we just try to understand the change, if you try to write a function that explains the difference, the sudden seasonality is going to add the noise to that function, right? It's actually the noise for us. Simple way to understand this. Suppose we just want to write a function that can simply make the forecast like this. So we can see the seasonality is actually the noise in order to uh, detect the pattern, in order to detect the trend. Yes. The trend is good thing for us if we try to analyze manually, but when we try to work with the statistics, where we try to write some parameters, some functions to explain the trend, in that case the seasonality, the sudden hike or sudden peak or sudden drop that we get on every season is actually something bad for the function. No, right? Isn't it? Isn't it? A sudden peak or a sudden drop on a equal interval of time is something bad for the statistical explanation. No? Make sense? Yes, guys? We'll see. We will talk about the algorithm and we'll see how exactly that algorithm is working. It's not going to work in a linear way that it use some other data to predict. It's not going to work in a supervised manner to use X in order to make the predict Y. If we want to predict Y by utilizing the X, it's not time series forecasting, it's a supervised learning. We can simply calculate the coefficient, beta coefficient, M, that how time is impacting Y, and we can make predictions. It's not time series forecasting then, right? That's a supervised learning in that case. If we use time, we want to predict Y with respect to time. So Y equals to M into T plus C is the straight equation, we can do all those possible transformation and get the predictions, right? So that's not a time series forecasting then. That's a supervised learning in that case. Now, right? Yes, guys? All good till here, everyone? So seasonality is something we don't want in our data, and stationarity is something we want in our data. Now let's come to the algorithm. Examples: predicting weathers, predicting sales with respect to the previous trends, right? Predicting weather forecasting, but the actual weather forecasting product softwares what we have, they take a lot of different factors also. That's not only time series forecasting, but if we talk about only time series forecasting, predicting sales without using any other parameter, only its past trends. That's the example of time series forecasting. Okay. Great. Now let's move and let's talk about the algorithm. So the algorithm is Arima. Stands for Auto Regressive Integrated Moving Average. Moving average. Okay, that's the name of the algorithm. So this is what we will be discussing. Arima. So before Arima, there was AR model, auto regression. There was MA model, moving average, right? And there was ARMA model, auto regression and moving average. And now the final version of this entire algorithm is this entire research was Arima, auto regressive integrated moving average. So this is what we will be talking about. Put on all the algorithms for time series. See, when we say all the algorithms for time series, in that case we call it as a sequential modeling, right? We call it as a sequential modeling. When we need to detect or when we need to work with the sequence in a given series, we call it as a sequential modeling. And for the sequential modeling, we have a very powerful networks in deep learning, like RNN, recurrent neural networks, GRU networks, gated recurrent neural networks, right? We also have long short-term memory networks, but those are the algorithms that we use in deep learning. Okay, so those are also the algorithms for time series or the sequential modeling. The time series analysis, time series forecasting. The sequential modeling is the parent term of this time series forecasting. Perfect. So this algorithm has three parameters. Like other algorithms were having some parameters. This is also having three parameters. AR, auto-regressive, integrated, and moving average. Now every element is carrying some significance. This is the P. Sorry. This is the D. This is the D. This is P, and this is Q. P, D, and Q. And we need to calculate the PDQ in order to train a Arima algorithm, auto-regressive integrated moving average. In order to train Arima, We need to calculate P, D, and Q for a given time series data. Then only we can train the Arima model. Now let's see how do we calculate the PDQ. First of all, let's see how do we calculate the D. Okay. First, let's talk about the D. Now, in order to understand what is D, D is actually the differencing. And what exactly is differencing? Let me take an example of a non-stationary series. 1, 2, 3, 4, 5, 6. This is a non-stationary series. Yes, guys? This Y is non-stationary. Okay. We calculate the difference of Y to make it stationary. Difference of Y. How do we calculate the difference? First value will become nan. 2 minus 1, 1. 3 minus 2, 1. 4 minus 3, 1. 5 minus 4, 1. 6 minus 5, 1. So now see difference of Y is stationary now, right? Another example, Y, we have 1, 2, no, I need to pick more random series. 0, 1 plus 2, 3, 6, 10, 15. Suppose this is another non-stationary series, right? This is another non-stationary series. We will try to do differencing here. We will try to do differencing in the series and let's see what happens. Difference of Y, this will become nan, this will become 1 minus 0, 1, 2, 3, 4, 5. Now see the difference is also not stationary. Yes, the difference is also not stationary. Yes, right. So what we do, we again do the difference of the differenced series, right? And now nan, nan, and then we will be having a stationary series, right? So how many times we are differencing will be the value of D. For this case, D will be 1. For this case, D is equals to 2, right? We did 2 times differencing, then only we got a stationary series. Here we only did 1 differencing, we got a stationary series. So integrated, the value of D is how many times we are differencing to make the data stationary. Easy? Easy? Awesome. So out of PDQ, D is clear to us, right? Out of P, D and Q, D is clear to us. Clear? Awesome. Awesome. Now let's see how P and Q can be calculated. So we can calculate the value of P by PACF, and we can calculate the value of Q by ACF. So PACF stands for partial autocorrelation function. Partial autocorrelation function. And ACF is called autocorrelation function. Okay. Partial autocorrelation function and autocorrelation function. That is PACF and ACF. Clear? So we will calculate the value of P by PACF and we will calculate the value of Q as ACF. Now let's understand what is ACF and PACF. First of all, ACF. So let me simply create a timeline. Today is Tuesday, right? Okay, let me pick Tuesday, then Monday, then Sunday, then Saturday, then Friday, right? Then Thursday, and again Wednesday. Make sense? Tuesday, Monday, Sunday, Saturday, Friday, Thursday, Wednesday, right? Let's suppose this is the timeline. Now, the value of Q, if the weather of today, that is Tuesday, if the weather of today, that is Tuesday, only depends on the weather on Monday. If it is only depending on the weather of Monday, the value of Q is 1. Okay? If today's weather, that is weather on Tuesday, depends on the weather on Monday and also on weather on Sunday, in that case, the value of Q will be 2. Right? And the third case, or there could be lots of such possible cases, if today's weather, that is weather on Tuesday, depends on the weather on Monday, also depends on the weather on Sunday, and also depends on the weather of Saturday. So the value of Q will be 3. Right? Right? So this is what autocorrelation function is. How many previous lags of information, our correct lag depends upon. How many previous lags of data points our current data point depends on is called autocorrelation function. Correct? ACF? Perfect. Now again, there is one more thing to notice. We won't be only talking about the Tuesday. We will observe this, correlation, this autocorrelation for Monday, Sunday, Saturday, everyone. Let's suppose Tuesday was having 3, but Monday was not having 3. So we are not going to use 3, right? See, what I mean to say is, suppose Tuesday is having correlation with Monday. Tuesday is having correlation with Monday, and suppose Sunday also. But Monday was not having correlation with Sunday and Saturday. Sunday was not having correlation with Saturday and Friday both. In that case, it won't be 2, right? Every observation should be correlated with last 2 observation. Yes? Again, if today's weather, that is Tuesday, depends on Monday and Sunday. Suppose today's weather depends on Monday and Sunday. Monday and Sunday are strongly predicting today's weather. But what was the weather on Monday does not depends on weather on Saturday. So then it's not 2, right? It was 2 only for Tuesday, but 2 was not true for the Monday itself. And again, we will see for Sunday as well. If the weather on Sunday also depends on the last 2 previous 2 lakhs or not, right? Then only this entire series has some definite ACF value that doesn't depends on this last information itself. The entire series should follow the same pattern. Then only we can utilize that information and make the predictions for future. Yes, then only we can make the predictions for future. Not only the last observation is important. We need to understand the pattern in entire series. That's how we will be making predictions. Make sense? Right? So So what is this ACF and PCF? This is all about detecting the patterns in the series, right? It's all about detecting the pattern in a series. Here we will calculate, and whatsoever it will be 1, 0, 2, 3, or whatsoever it will be for a given series, we will use that value as a value of Q. Okay, we will simply observe, we will see whatsoever is the pattern, whatsoever is the relation, autocorrelation, we will simply give that value to the Q, right? What if Tuesday was dependent on Sunday? Tuesday was dependent on Sunday and not Monday. No, it's if there is a time series data, we need to identify the autocorrelation, and in that case, if it was not related on Monday, we won't even check for Sunday, right? If it's not depend on Monday, we won't check for Sunday, right? How can the pattern be same for every day? It has to be same. If see, when it comes to a time series forecasting, or whenever someone is doing intraday trading, we try to detect the pattern for a given look back period. If let's suppose I want to trade for next 2 hours, I will decide some look back period that I need to analyze the data for last 15 hours or last 30 hours in order to make a strong analysis about the next 2 hours, right? Yes. So that look back period, that last 30 hours should have some significant relationship, some significant pattern. Then only I can analyze about next 2 hours. Yes? Make sense, guys? Does this make sense? Suppose I am doing intraday trading. I have invested in a stock. I need to trade for next 2 hours. So in order to make a good decision for upcoming 2 hours, I need to analyze that pattern for some look back period. And let's suppose my look back is 15 or 20 hours. So there should be some significant pattern in those 15, 20 hours. Then only I can make a good analysis and a good forecast about the next 2 hours. What if pattern currently changed in the present time? So that is something we won't be able to predict, right? If we talk about the predictions, that see, your question is like we build a model for predicting the sales, but suddenly demonetization happened, right? The question is like we build a model to predict the sales on the previous trend, but suddenly demonetization happened. So that is something our model won't be able to capture, right? Make sense? Make sense? Does this make sense? Right? Okay, what is ACF? Is it clear, guys? What is ACF? Perfect. Now, once this ACF is clear, let's understand the PACF. Let's understand the PACF. Okay, so P equals to Q. Now, it's not Q, it's the value of P we are calculating here. ACF is autocorrelation function, how many previous lakhs of observation our current observation is depending upon. That's the autocorrelation function. Okay, great. Now the value of P. So now in case of P, we don't include the in between observations. So if P equals to 1, it means weather on Tuesday depends only on Monday. If P equals to 2, it directly depends on Sunday. The Monday is not included in that case. And if P equals to 3, this weather again depends on Saturday. Correct? Easy? ACF and PACF, got the difference? Yes. Yes. Perfect. Perfect. Yes. This is called partial autocorrelation function. Partial autocorrelation function will not include the in-between points. If the value is 1, the last 1 lakh, the value is 2. The previous second lakh, the value is 3. The previous third lakh. That's how it's gonna be. That's how it's gonna behave. Okay. This P and Q will be given by us to the algorithm. Exactly. And we have libraries in order to analyze the values of P and Q on a given time series data. Okay. Perfect. Now let's do the code, guys. Let's work with some case. And right now, what we will be discussing is champagne sales. Drive. We are using this one, Jan 3, no, not this one. This one, 7th Feb. 7th Feb. Yes, sure, wait a sec. Today's day 12, right? No. Yeah. Uploading the data in day 12, guys. Download and open this file. Let me unmute you. Yes, please.
Some notes I'm preparing.
I'm sorry.
Can you hear me?
Yes, yes, yes. Now we
Yeah.
can.
Actually, I'm preparing some notes. Actually, so for that, I might have done some mistake in the note preparation. I would like to, I would like to have your help in that.
Okay, okay, sure.
One is that, and second is I have some real-time query.
Okay,
It's on my day-to-day project. So at the end of the
sure, sure,
today's
sure.
session, let's
We'll discuss
yeah,
that.
yeah, yeah. Thank you. Only those two.
Perfect. No worries. We'll discuss that. And regarding the notes, you can share it through Google Drive or GitHub or anything. You can just upload it
Uh,
somewhere and you can share the link with us. We can have a look.
okay, okay. At the end of the session, I'll do this.
Yeah, yeah.
Yes,
Perfect.
yes, yes. Thank you.
Perfect, guys. Yes. Please download all these things. You know NLP. You're asking like about NLP. Do you have any questions about NLP? Do you have any questions about NLP? How it's useful? It's very useful. A small example of NLP is a chatbot, right? The engines or the search engine optimization, how Google works, to return us the results. That's also an application of NLP. So NLP is very useful. Very, very, very useful. Whenever we have the textual data in order to work, see, machine learning we understood. In machine learning, we mostly deal with the numerical data, but whenever we have the textual data, some text, some documents, we use NLP. Yes, we need to learn it for the job. Yes, we need to learn it for the job. Okay, please download this file. Let me know once it's downloaded. We have it. We have it. We have the natural language processing in our module. Here, let me show you. If you see this text mining, this is all about NLP only, Natural Language Toolkit, NLTK. Yes? Have you gone through with this self-learning section? Yes? So, have you checked this text mining lesson 1, where we have text extraction, text processing, stop word, stemming lemmatization? Not yet? Okay, even if we don't see the videos, even if we don't go through with the videos, the topics, the headers are there, NLP, process, workflow. So this is actually a proper chapter, a proper module for natural language processing. Yes? Haven't you checked for the syllabus before enrolling in the course? Yes? So it was there. NLP was there, right? These topics must have been mentioned. If you have checked, all these topics must have been mentioned in the syllabus, in the course curriculum. Yes? These topics were not there. I doubt actually, because if these topics are there in self-learning, they must be available in the course curriculum as well. Let me check. Yes, guys, downloaded everyone? Yeah, please. You can start. See, after this, we will be doing natural language processing. After this, we will be doing natural language processing. I see the text mining is right written over here. Once we complete this, we will be having the NLP sessions, 1 or 2 sessions, in which we will be talking about the text pre-processing and classification and other things. So after that, you can use that elective part of this course. We also be doing this thing. Yes, I can see this course curriculum, text mining, and everything mentioned right here on the website. My phone number? How so? Oops. Oops. I didn't open anything. I didn't open anything. Okay. So let's start the Arima and seasonal Arima. Okay. So let me just erase all the outputs. I'm not in this. I'm so sorry, guys. I'm out of this discussion. I'm out of this discussion. Okay. Okay. Let's come to the Arima and seasonal Arima. Yes, I can share my LinkedIn. I can share my LinkedIn. What are checkpoints here? Checkpoints. Sorry. These checkpoints when it was last saved. When it was lastly saved. You can ignore the checkpoints. Okay, if the checkpoints are also there. Okay. So checkpoints are just the track of its versions. You can ignore. We just need to download these two files. You can ignore the checkpoints. Okay, you can simply download these two files. That's also some supporting files. You can ignore that one also. Okay. Now, importing the libraries, matplotlib, pandas and warnings, and numpy. Some basic libraries here. Okay. So, there is a read CSV and there is a head of the CSV data where we have the champagne sales. There is a lot written in the column label, but it's the champagne sales, nothing else. Okay. Monthly champagne sales. We have the monthly champagne sales. That's our data. Now, if we check the shape, we have 107 records and the data is monthly. Okay, so how many years we have in this data? This data is for how many years? 107 are the months. Approximately 9 months. The table of 12 nines are 108, and there are 107 records. So 1 month less than 9 years. Okay, so let's check the missing values. Now we have the last two records missing, where, okay, so yeah, this is the time series data. Last two records are missing. What we can do, guys? The month is also not in a proper format. Drop. So we will simply drop. And this is how the data looks like now. Okay. Then data frame, this is month and sales. D types. Okay, if you see the month as object, if the month were there, we would do mean for missing. No, these are the last two records, so it's better to drop them. If there is something in between, then we can think of something, but they are at the end. So let's simply drop them. So month is object, we need to convert this month to date time. We are simply converting month to date time. And this is how the data looks like now. Okay. Easy? Yes, guys, easy so far? Perfect. Now we will simply set this month column as the index of the data, and we will be good to start our analysis. So we simply set the index as months. We simply set our index as months. We removed previous index. Yes, 0, 1, 2, 3 and all, they got removed. They got removed. Perfect. So that's the data. Now when we do plot, it will simply display the trend. Okay, now let's talk about the stationarity, and let's talk about the stationarity first. Reset index function, there is a reset index function that can reset this index and again give a default value. We created month but still in date format. Sorry, I didn't get your question. Yeah, this is having the seasonality, stationarity both. Means stationarity is not there, seasonality is there. That's like both of the things are not in our favor. We Okay, can you please tell me which cell you are talking about? Are you talking about this? So what we are doing here, the month column, there is a column month that was an object type. We simply converted it to date time format, and now it is in date time, right? Line number 10. This was the previous value of month, but once we converted it into date time, this is how the month would look like. So it will it will convert it into a default format whatsoever is the YYMMDD. This is the default format. So YYMMDD, it got converted to YYMMDD. If you want to change it, we can use string format to change the format, right? Yes, guys. If we want to change the format of the date, we can use simple.str format function, and we can change the format. We can we can place the month in the beginning. We can place the year at the end, whatsoever we want. Easy, clear? Okay. Strf time, string format time, is the function. Yes, all good with this part? All good with this part, everyone? Okay, awesome. So now let's come to this. So visualized way of understanding the stationarity, seasonality is obviously the method, but again we have a statistical test called Dickey-Fuller test. ADF, Augmented Dickey-Fuller test. So this is a statistical test that can tell whether a data is stationary or not, in which null hypothesis the null hypothesis is the time series is not stationary, right? Null hypothesis means not stationary, and alternative hypothesis is stationary. So what kind of p-value we want? Augmented Dickey-Fuller. Augmented Dickey-Fuller. Perfect. So we simply created a small function. We are invoking this ADF value, and we are checking if the p-value is less than 0.05. We are saying it's stationary. Otherwise, we are printing it's not stationary. Easy. We are taking the sales data. We are passing through the ADF test, AD-Fuller function. If the p-value is less than 0.05, we are saying it's stationary. Otherwise, we are saying it's not stationary. Right? So let's see what this function tells about this data. So it is saying it's not stationary, and also by the this kind of trend we can say it's not stationary, right? So this was the initial stationarity check on the data. Clear? Awesome. Now what we should do in order to achieve stationarity? Less than 0.05 means more than 95% of the confidence interval, right? Less than 0.05 means more than 95% of confidence level. Okay, now the second step should be to convert them to stationary. Now, how do we convert it? So simple, we discussed the differencing method. Here it was. Yes, here it was. The differencing. So how exactly we did it? The second value minus first value, third value minus second, fourth minus third, and so on, right? That's how we did the differencing. Right? That's how we did the differencing. Yes. So we can use shift in order to achieve this. So first of all, just observe what shift 1 is doing. Only observe this output, and see what shift 1 is doing. Yes, what shift 1 is doing? It's not differencing. No, guys, it's not differencing. It's shifting the index. It's shifting the index. Yes, it's shifting the index. Now, when we subtract with shift 1 with the actual value, actual series, then we will get the difference series, no? Now when we do the subtraction on this, we will get the difference series, right? Means when we simply do df sales minus sales dot shift 1, now it will give the difference series, right? Perfect. So let's store, and okay, this is the plot, and if we check ADF test is saying it's a stationary now. So one differencing made the data stationary. The value of D is going to be 1, right? Perfect. So we did difference only once. We only did difference once, and after doing the difference, this is how we calculate sales first difference, by simply doing sales minus sales dot shift 1. This is the difference data we received. This is the difference data we received, right? We can simply plot it also here. What is shift here? Okay. See, this was the actual information sales, and this is what shift does. It will simply shift one index, right? 2815 is the second value now. 2672 is the third value now. It will simply shift the information by one index. And when we do the subtraction, we will get the differenced data, right? Right? Last row will be there. The second last will become the last. See, the second last became the last, and the last vanished. Yes, the second last became the last, and whatsoever was the last is not there anymore. Okay. How can we change the data when the shift is used? Again, I didn't get your question. Like, what kind of change we want to make? So after doing the shift, if we subtract sales minus sales dot shift 1, we will get the difference series. The value of the second row is changing by the first. Exactly, we do the shift. See, we want to subtract this. We, in order to make the difference, we want to do 2672 minus 2815. That's what we want to do. Then 2755 minus 2672. That's what we want to do. Yes, that's what we want to do. Yes, okay. Now this is the sales data, this is the shift data. This will become minus 9, and this will become minus 2815. 2815. This minus 2672. 2672. So see, we are actually getting the same thing. We are doing the same thing. Yes. Yes. Is it still confusing? Again, let me explain again. In order to get the differencing, we simply need to calculate the difference like this: 2672 minus 2815 and 2755 minus 2672, right? Then 2721 minus 2755. This is what required. This is what required, right? Okay. If we check this, 2 minus 1, 1, 3 minus 2, 1, 4 minus 3, 1, 5 minus 4, 1. That's what we did. Here also 3 minus 1, 2, 1 minus 0, 1, 6 minus 3, 3, 10 minus 6, 4, 15 minus 10, 5. That's what we did. Yes. Similarly, here also we want to do this. We want to achieve this. And if you subtract sales minus sales dot shift 1, so it will go like minus 9, minus 2815, minus 2672, minus 2755, and this is actually the same thing we are getting. Understood, everyone? Perfect. So, sales minus sales dot shift 1. Clear, everyone? This will give the differential data. We simply did the plot on the different series, and we also did the ADF test, and now it is stationary. Yes, now it is stationary, right? Perfect. So we understood the stationarity. We have a stationary series now. The series is stationary now. And what's the value of D? 1. Because we got the stationarity after one differencing would be. Yes, clear, everyone? P value is 2.5 E minus 10. Please observe this. So this means this is scientific notation of numbers. right? It's a fraction divided by 10 raised to the power minus 10. How to get know what is the value of d? Every time we have to manually check this. Yes, we need to do the differencing. We need to check whether we got the stationary series or not. That's the only way to check the value of d. But to check, but to be stationary, the values after differencing should be constant. It's actually not possible to get the constant. We can also accept the stationarity if there is, like, the time cannot explain the trend, right? The time cannot explain the movement, and the series also, the time won't be able to explain the movement, right? Or I can say the moving average is constant, the moving average is same here. The seasonality is still there. The seasonality is there. We haven't treated the seasonality yet, but stationarity is something we are talking about right now. And we are done with the stationarity part, right? The stationarity is something we have achieved, and also one value of one parameter of the Arima PDQ. Perfect, guys. Yeah, let's take a break, and we'll continue after the break. Stationarity depends on difference, not exactly. Difference is a way to get the stationarity, and not only the difference. There are a lot of other methods also, but most of the cases difference work. If we have the exponential series, we need to do log and then difference. But difference works in most of the cases. Square root can also be a case. We can do square root, we can do the log and then difference. Depends upon the data. If the data is exponential, if the series is exponential, then we do the log and then difference. Otherwise, this would work. Okay. We'll see how after the break. How will we remove seasonality? We'll see after the break. The next step will be to decide the further parameters d and p and q, and then after that we will do the seasonality and other things. There are two types of algorithm, Arima and seasonal Arima, so we'll talk about that. Perfect, the polls are open, guys, and let's do the timer. Hey everyone, everyone is back now. Perfect. So now let's proceed and let's talk about the ACF and BACF. Let's proceed and let's talk about the ACF and PACF. So in order to get the values of ACF and PACF, we can simply use the ACF function and PACF function from statmodels.graphics library, and this will give two ACF and PACF plots. Okay, this is giving the ACF and PACF plots, right? This is how the plot looks like. Now based on this plot only, we need to decide the values of P and Q. So this will be the value of P and this is going to be the value of Q. Okay, so how do we decide? Starting from the very beginning, we just need to see how many lags are above the shaded region. How many lags are above the shaded region? Okay, how many consecutive lags? Sorry, not only the lags. How, starting from here, starting from this point, going to this direction, we just need to check how many consecutive lags are above the shaded region. If there is anyone that's not above, we will not proceed further. Right? We need to count how many lags are above the shaded region. We need to count how many these lags are above the shaded region. If consecutive lags, we just don't need to count from anywhere, just the consecutive lags. Just the consecutive lags. If there is anyone that's, see, the second one is not above, we will not proceed for the next. We will only stop at this point. If this one was also above, then it would be 3. First, second and third, fourth is not there, so we won't proceed further. Then it would become 3. Right? First is there, second is there, third is above, fourth is not there, so we will stop at this point only. We won't proceed next. Should be above the shaded region. It should be above the shaded region. So we just need to check the consecutive lags above the shaded region. Consecutives. If at any point, if the lag is not above the shaded, we should not proceed further. We should not look for the next. So Q is only 1. There is only one value, right? So we will make it 1. And also P is also 1 here. Q is 1 because there is only one value above the shaded region, right? Again, forget it was 1. We just need to count how many lags are above the shaded region. How many lags are above the shaded region? Consecutive lags, not like after a break. The lags, the continuous lags that are above the shaded region. How many continuous lags are above the shaded region, guys? Yes, how many continuous lags are above the shaded region? Above shaded region. Above the shaded region. Continuous. Continuous. How many continuous lags are above shaded region? How many continuous lags are above shaded region, guys? Got it? How Q will be 1? Lags, L-A-G-S, lags. Okay. Yes. So this is ACF and PACF plot. This is giving the autocorrelation and partial autocorrelation function. Remember we talked about that if there is a significant correlation or autocorrelation for all the series, then only we will consider. If it was there for this, but it's not there for this, we won't check for the further, right? It is a significant correlation at here, but it's not at here. So we will not check for all these things, right? X-axis is the lag, the previous lags, the previous data points, and y-axis is the autocorrelation, right? X-axis, X-axis is the lags, how many previous lags we have, and y-axis is the autocorrelation, and here it's a partial autocorrelation, right? Yes, but we need to count the lags with some significant autocorrelation and partial autocorrelation. What is significant? Above the shaded region. Consider this shaded region as a benchmark. So we will only consider it as good if it is above the shaded region. Shaded region, suppose like it will calculate the shaded region by some formula as a significancy, as you know, it should be above, then only we will say it's a significant, right? Right? So how many consecutive lags are above the shaded region? There is only one, right? Right? So the first one is for autocorrelation, the second one is for partial autocorrelation, the ACF and the PACF value. Sorry, the ACF and the PACF value. I don't know how to read this graph, how this is creating lags. We just need to learn how to read it and how to decide the values of Q and P. That's it. That's all we need to understand out of this graph. Okay? Perfect. Now, just tell me how many continuous lags are above the shaded region. 1. That is the value of Q. That is the value of Q. Yes? And this y-axis is the value of PACF. Here, sorry, it is ACF. For this, it is autocorrelation. This is ACF, and this y-axis is PACF. This y-axis is PACF. Right? Okay, now let me know if this thing is clear, how we decided Q equals to 1. Everyone? Also, Also, if we go in this direction, for the same PACF, the value of P, we will read it in a same way. How many continuous lags are above the shaded region? Yes, how many continuous lags are above the shaded region starting from here? Also 1. Also 1. Right? Because the second one is not above. If this was like this, then the value of P would become 3. The first is above, second and third. 3 are above. So we would take it 3. But right now, it's 1. Right? Exactly. So the order of PDQ is 1, 1 and 1. Right? That's the order of PDQ. I'll explain the code. Sure, I will explain the code. If this would, like, if this line is like this, then it would be 3. This is above, this is above, this is also above, this is not above. Then it would become 3. It's, it is in which one is below the shaded region? I'm saying if it is above the shaded region, then the value of P will become 3, right? Yes. Perfect. But right now it's only 1. But right now it's only 1. Exactly. Same will be there for ACF also. The same thing, the same logic will be there for ACF also. Okay. Perfect. How to read ACF and PACF? Is it clear? Perfect. Now let's see the code. Okay. So there is a function ACF and there is a function plot PACF, right? Okay. Yeah. Out of the shaded region. Cool. Yes. Above because this is below, right? Understood. It should be out of shaded region. Yes, it should be out of. I was saying it incorrect. It should not be only above. It should be out of. My bad. It should be out of the shaded region. Okay. Now is it clear, everyone? Now is it clear, everyone? Perfect. 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 Okay. Now let's see how exactly this code is working. So do we know the subplot concept? Right? Okay. So we are simply creating two subplots, right? So axes AX1 and AX2 are basically to decide the subplots. AX1 and AX2 is basically to decide the subplots. Okay. Two one one. That's with respect to the figures. Suppose we want to divide it like this. So this figure has two rows and one column. This will become 211. This will become 212. Right? If we want to divide a figure like this, it will be 1, 2, and this will become 1, 2, 1 and 1, 2, 2. Okay? Perfect. So that's how we specified the subplots, and we simply given the figure for a specific subplot. Okay? So plot ACF, we have given the data and we have specified the previous lags where we actually want to, how many, what exactly look back we want to go for. So it is checking for 10 previous lags, right? We had specified 10 here. So it is, that's why it is going for the last 10 observations. Okay. 10 is more than enough, right? We can increase it also. So we just need to see how many previous observations we want to check, whether there is any correlation or autocorrelation, partial autocorrelation or autocorrelation. So 10, 20, 15, just pick a that number that the autocorrelation should not exceed than that. Yes. If all the legs were out of the shaded region, if all the legs were out of the shaded region, then we might increase this previous legs and read this figure again. Okay. But right now we are not even going after the second one. So 10 is also quite huge. Perfect. Clear? Clear, guys? Awesome. Now we got to know the all parameters like P, D, and Q. Everything is one here. The order is 1, 1, and 1 for us, right? So P equals to 1, D equals to 1, Q equals to 1, importing the Arima model and simply creating an object of Arima where we specified the sales data and we specified the order of Arima. Okay. Can you show D? Sorry, D. We don't see D by this plot or something. What was D, guys? What was D? How do we decide the value of D? The differences, right? And how many differences we made in order to achieve stationarity? 1. Correct? And you mean to say this code? This code? Show me if we got the value of 1. Okay, so can you show me if we got the value of 1 for D? We did one difference here. This was the differenced series. Okay, first of all, let me explain what was D. So did you understood that D was 1 in this case and D was 2 in this case? Did you understood that D was 1 in this case and D was 2 in this case? Yes. So now what is the definition of D? What do we understand? What exactly is D? How many times we are differencing to make a series stationary, right? How many times we are differencing to make a series stationary? Yes, we did differencing only once and got the stationary. Awesome. Awesome. Perfect. Now we got the PDQ1, 111, right? We got the PDQ1 and we simply created an Arima model by giving the sales data in the order of PDQ. Now see here, why we are giving sales and why we are not giving first difference? Because we have given the D value, right? We have given the D value. Yes, we had given the differences, how many times we need to difference. So we don't need to give the difference series here. Perfect. Now we will simply do the fit and we will simply plot the actual and predicted values. So see, this is the actual data and this is what we get as a prediction. Yes guys, this is the actual data and this is what we get as a prediction. So we did all that analysis, all that study for this. Interesting? We did all that PDQ, ACF, PSCF plot and everything to get this prediction. That is nowhere close to the accurate actual values. The start and stop is from where to where we want to make the prediction. So like it has started predicting from here. So this was the 90th observation and it stopped here. It was the 103rd observation. Okay, perfect. Now this prediction is nowhere close to the actual values. The forecasting is nowhere close to the actual values. Yes. We need to tell some start and stop whenever we do the predict. So we need to tell from where to where we want to make the predictions in the data. So 90th to 103rd observations we are predicting. Okay, from 90th observation to 103rd observations we are predicting. Okay, now we can see this. These predictions are nowhere close to the actual numbers. The predictions are nowhere close to the actual numbers. Yeah, we can do from 0 to 103. Oops. Oops, oops, oops. I think start must be greater than equal to value forecasting got 0. It should, we cannot give that smaller value. Let me try to reduce it more. Yeah, 80 is also something we can. We cannot predict from the very beginning. Okay, so again, if you use 80 itself, it's nowhere close to the actual values, right? It is nowhere close to the actual values. Great. Great. So now the predictions are not correct, but let's try to understand what went wrong. Remember the concept of seasonality we discussed? Yes? Remember the seasonality? Perfect. And we haven't treated the seasonality in the data. The seasonality was there. That's why the Arima is unable to perform, right? Right? Okay, if we get some earlier predictions, still there is nothing like that. Or whatever we can give, we are not actually getting the right results. Okay, so this was the sales first difference. This was having the seasonality and we haven't treated the seasonality, right? This was having the seasonality and we have not treated the seasonality. Yes, guys? Perfect. So, how do we remove the seasonality? Just do the differencing with the order of seasonality. So earlier we did the differencing with the sales dot shift 1 only, but now we are doing differencing with the sales dot shift 12 because the data was, the pattern was getting repeated after every 12 months, right? The data is, the pattern is getting repeated after every 12 months. So we simply do this sales minus sales dot shift 12 and we will get this. Now we can see there is no seasonality, right? There is no seasonality, right? Perfect. So if we check the AD Fuller test, this is also stationary. 12 is the order of seasonality. The pattern is repeating after every 12 months, right? 12 is the order of seasonality. The pattern is repeating after every 12 months, right? Great. So it's stationary too. Now we will be implementing the seasonal Arima. No, we need to know the pattern. If we don't know the pattern, then we won't be able to treat the seasonality, right? We should know when exactly. See, if there is a seasonality, means it is repeating after a specific season. So we can easily detect the pattern, right? When it is repeating. The seasonality is what? Whenever there is a specific repetition of a pattern over a given interval of time. So what is that given interval? That is the order of seasonality. And if there is a seasonality, there will be some order of seasonality also. If there is a seasonality, this order will definitely be there, right? Perfect. So now we are implementing the seasonal Arima. Now we are implementing, instead of Arima, we are implementing seasonal Arima. Okay. Now in seasonal Arima, instead of only giving PDQ, we are also giving the seasonal order where we have PDQ and the order of seasonality, that is 12. Right? Now we are training the seasonal Arima model. Now we are training the seasonal Arima model, right? And in seasonal Arima, along with the values of PDQ, we are also giving the values of PDQ plus order of seasonality, right? So after training, if we make the predictions now, Now the actual values and the predictions are quite close, right? Now the actual values and the predictions are quite close here. No? Correct? So why we were not getting the good results earlier? Because of the seasonality. We have treated the seasonality, trained seasonal Arima model, and now we are having some decent results. Clear? Sure, let's see. Yes, close enough. Not too good, but not even that bad. Right? Awesome. Perfect, guys. So, all good with the Arima and seasonal Arima model. Treat the dataset if it's not in proper time series. Say a few months data is missing. In that case, we do the resampling. In that case, we do the resampling. There is a resample class that can resample the data and fill the missing timestamps. Upsample and downsampling. Upsampling and downsampling uh, are basically the concepts that we can apply on the time series data in order to make the data more, no, not forward fill and backward fill. Linear interpolation, there are other like moving averages and linear interpolation kind of things that are being used. And downsampling and upsampling can also retransform the scale. Suppose we have the data on hourly basis, we want to get data on monthly, or not hourly to monthly. We have hourly, we want to get minute wise transformation. That's called downsampling. We have the data every minute, we want to make it hourly. That is also we can do with the resampling library. That is also we can do with the resampling library. Correct? And that library can also help us to fill the missing timestamps as well. But it should not be too much uneven. Means if few of them are missing, then dealing it with the resample class is okay. But if there is a lot of uneven data points, then resampling will also won't be able to give some good results, right? Preconditions that are the stationarity and seasonality, right? So first of all, it should be in equal interval of time. Second of all, it should be stationary, and it should not be having any seasonality. So there are only three things. It should be in equal time intervals. It should be stationary. There should not be any seasonality. The three things that we need to check. For the stationarity, we have ADF test, augmented decupolar test. For seasonality, the visualization is the only way. We need to plot and we need to check whether it's seasonal or not. Okay. Yes, guys. Any questions? Anyone, please? For equal intervals, we need to use some logic in that case. If we have the timestamp, just if it is in months, calculate the difference. If the difference is one only for the entire column, create a new column, calculate the difference. If it is months, just calculate the difference, time difference. If it is one for entire difference, it's in equal intervals, right? Yes, for making the future forecasting, we actually need to create new dates. So this date offset function will be used to create the new dates. So this is the last date, right? So when we do date offset month equals to 1, it will create the date for the next month. When we do it month equals to 2, it will create a date for the next 2 months, right? Df dot index minus 1, that's the last month. That's the last month, last date what we have in our training data. Yes. Now last month plus date offset months equals to 2. So this is 2 months next to the last month. So we are simply using a list comprehension df dot index minus 1 plus date offset months equals to x, right? For x in the range 0 to 24. So we are creating next 2 years of the dates, right? This will create next 2 years of the date. See? Yes, we can do same for the year also. We have months, we can change this months to year and we can offset for the years also, day, year, anything. So we are creating next 2 years of the date, right? Now we are simply creating a data frame for the next 2 years, and this is the future data frame in which we have the date for the next 2 years and nothing else is available for us. We only have the date and nothing else is available. We will make the forecasting for this data. This is the predictions, the forecast for next 2 years. But before we make the forecasting, we need to generate the dates. We need to generate the dates before we do the forecasting. Clear, everyone? Yes. So we are plotting this forecasting. We are making the forecasting on future data frame, right? This is a data frame. So whatever results we are getting, that is a data frame that will be stored in a data frame. Yes. That's the data frame. Future DF forecast. It should be in the last values. We can simply export this dot with .2 CSV and it will be exported to Excel. Everything is stored in a data frame. We can simply do the 2 CSV and it will be stored in a data frame. Okay. Let me re-execute it and let me check the future data frame. Okay, wait a sec. Why the values are not coming up? Am I checking the same data frame? Okay, so when we are plotting, we get the data in forecasting, but why we are not getting the results over here? 128 is the total length, 111 are the missing values, means yes, we have the data in forecast. So future df, where future df dot forecast not null. Let me just show you guys. Dot is null. We want to apply the not. Okay. So these are the forecastings. These are the forecasted values for these dates. Okay. So we can simply export it to Excel by doing 2CSV and give the parameters or how the CSV works, right? The predictions we are storing in the future DF forecast column, and we can simply export this to the Excel and we are good, right? Perfect. The train and test. Okay, sure, sure. Yes, guys, all good till here, everyone? How much time did you took completely to learn ML? I like the curiosity, but ML is a very huge topic, and I'm still learning. If I tell you honestly, it's a very huge topic. ML, data science, deep learning, and right now also, I still used to get some new things and new logics and new libraries. It's been 4 years. I've been working on this domain, data science, ML, and everything. I would say I'm still learning all these things. It's huge. It's very huge, guys. It's very huge. Yes. In AI topics, myself, it depends. Like if I need to rate in during an interview in front of a manager, or do I need to rate uh, like in front of someone who is recently learning AI? So it completely depends if the person is more experienced, or, or if the person is still learning. I asked because I am facing difficulty in learning it. There is no shortcut if I try to answer your question very, honestly, there are no shortcuts. Only the practice, only, you just need to practice, you just need to give more time in exploring and doing the things, right? It's the practice, practice, and practice. Okay. Yes, guys, makes sense. And in AI, in ML, everything, honestly, if I would rate myself out of five, I will put it somewhere in between three to five, three to four. I won't say five, I won't four, somewhere between three to four. Like this is what I'm confident on. If we talk about the entire AI concept, because AI is a very huge. I have some experience working with the reinforcement learning agents. That is where the actual AI implements. In deep learning and machine learning, I'm pretty confident. But if we talk about the overall AI, that includes a lot of other domains as well. So I'm yet to explore those things. I would rate Oracle out of five. No, I cannot accept this. If you have more than 20% of 20 years of experience, definitely you have a good exposure of these tools. I wouldn't accept two as out of five. You have a lot of, you know, you must be having a lot of exposure on those domains. No, I'm not a full time teaching. I'm not full time teaching. Practice, guys. There is nothing else. There is no shortcut. There is, no specific suggestion for anyone with the different background. You just need to practice. You need to explore. You need to rewrite the problems. You need to implement the codings. Read about the mathematics and everything. There is nothing else for anyone. If anyone is facing difficulties, please try to spend more time in reading the logics, the concepts, the mathematics, and the problems. Hacker rank, Kaggle is there. That's the only way. That's the only way, right? We just need to give a proper time here. Okay, let me just quickly show you how to work on the train and test data. You will get the idea. Why null values? We are actually only displaying the data where forecasting is not missing. We are checking this code will only give the data where this column is having some numbers, because this data has lots of records. This data frame has lots of records. So this code will only give those values where forecast column is not missing. Okay, so if I show you the Big Mart sales V2 problem. Okay, so see, we only read the train data here, right? Bigmart train.csv. But if we see, we have bigma test.csv also, right? Let me execute all the codes. So see, we are following some methods to treat the data, right? Okay. So right now we are splitting our x and y. So at this point, when we are splitting our x and y, we need to import the test data. Okay, now if we see test dot info, this will not be having, this is the test dot info, and this does not have the item outlet sales, right? This does not have the target. Okay, perfect. Now in item identifier we have already dropped, so we will drop the item identifier from this data set also. Item weight, it was missing and we have used grouped mean, right? So we need to fill the item weight with the exact same strategy what we have used earlier. Fat content, we need to check for the categories, rename the categories as we have done in training. Create the visibility bins. Okay, on the same benchmarks we have used on the training data. So right now we don't need to analyze in this case. Whatever we did in training, exactly same thing needs to be implemented over here without doing any analysis, because this is unseen data. We don't have this data in collection to analyze and study and decide. So whatever we have analyzed, whatever we have decided on train, exactly those things should be implemented over here, right? At the end, when we split this, when we have the x, so the columns and the data in x should be exactly same as the data in test. So whatever we have here in x should be exactly same in whatever the structure, the format, the pre-processing we have done in the test. So they both should be having the same structure of the data sets, right? The x variable here and the test data here should be having the same structure. Make sense? The name of columns, the number of columns, the data in a column, everything should be similar for X and the test. At the end, when we will train, see, here we trained. Now here we can simply, we should be able to do lm.predict test data what we have read there from the CSV. We should be able to do lm.predict that test data. We should be able to do the lm.predict on that test file after the training. And whatever predictions we are getting over whatever predictions we get at this point, we need to append those into a CSV file, and that's how we insert. That's how we suppose. Yes, instead of lm.predict x test, instead of that x test, we will be giving that information, that data what we have read from the test file. Correct? Correct? That's how we need to treat the test files. We don't need to get the scores. We will simply make the predictions and we will submit them. If like we used to get it during the hackathons, and we just need to make the predictions and we need to submit them. Okay? If we apply PC and train, should we apply in test 2 before model.fet? Yes, we should apply it on test as well, but test data will not be utilized in fit. Test data will be utilized in predict. We will give the test data during the predict. But whatever is the format of X in fit, that should be exactly same in predict. Otherwise, it will not work. So whatever we are doing on training, we should be doing exactly same thing on testing also. Okay? No, it will not look different. So in train, if you have transformed to 330 principal components, you will not be analyzing what are the explained variance ratio and everything in test. You will be directly transforming it to 331 principal components with the same PC object what you have used in training. So in the test data, we should not analyze and make a decision. Whatever analysis we have done on training, exactly same decision we should be applying on the test data. Test data is something we are getting on a unseen, right? So we cannot analyze the unseen data. We just need to do all the operations what we have done on training. We need to implement it on testing and make the predictions, right? Correct? Perfect. Yes, let me know if there is anything else, anyone. The model is created based on PC of train, but the predict is done on actual data of test. Will it predict perfectly? Okay, so in order to answer this, we need to understand why we create a machine learning model. Yes? Anyone guys, why exactly we create a machine learning model? Anyone please? What is the aim? Why exactly these algorithms are there? Why do we need to build a machine learning model? To predict on unseen data, right? To predict on some data that's not there. For example, we are building a model that can detect the cancer, right? There is a model that can detect the cancer, right? We have the data for our past patients. Suppose we have the data for 200 patients. Out of them, few patients were having cancer and few patients were not having cancer. We will train our model. We will train our model on those patients, on the past patients, 200 patients. We will get someone new. Now there is some new patient walked in. We will calculate the medical factors, whatever were important. We will give those medical factors for this new patient to our model, and the model will give the predictions, right? Right? Yes? Okay. Now suppose, let me create another one. Suppose while training we have the data for 200 patients, right? We have the gene values. Okay. So we have the information about the genes of 200 patients, and let's suppose every single gene consists of 20,000 length of vector. Okay. Suppose a single patient, the gene of a single patient is a vector of 20,000 numbers. Possible? Possible? And we have such 200 records. Possible? Yes? This makes sense? Okay. We did PCA here, and after doing the PCA, let's suppose we got 250 values only. Now we have 250 for 200 patients. Okay? Right? Perfect. So whenever there is a new patient came, one new patient with the gene, we have the information about its gene that is a vector of 20k numbers. We will be using the same principal component, we will be using the same PCA and transform it to length of 250, right? Yes? Yes? We are using the same PC object. We are using the same principal comp. We should not analyze this new patient again and decide how many principal components should be good for this new data, because the data should be exactly in the same structure in what we have trained. So we should not be analyzing and deciding the number of principal components again for this new patient. If we have done 250 for the training data, this should be done 250 blindly without any analysis, right? Make sense? Because the data what we have used for training, if a model is taking some 250 numbers, right, some 250 numbers to make the predictions. So like if the model is taking 250 values and also the cancer to learn, so during the predictions also it would expect exact 250 features whatever we have for the new patients. So without any analysis or something, we should blindly transform this 20k records to 250 principal component from the same object what we have used in training, right? Understood? Understood? We don't need to check 0.95 for the test. That's what I'm saying. We don't need to do any analysis on the test data. If it was 250, we just directly need to transform this to 250 without observing what is the 95 percentile or whatever it is. If it was 250 in training, exactly 250 needs to be done on testing without checking whether what's the 95 percentile or what. Okay? The testing data, we don't do any analysis, any study on the test data on the new data. Whatever we have done on the training, that needs to be implemented as it is on the testing data. We will simply specify, and we don't even need to specify. We don't even need to specify. What we do, where is the PCA code? Where is the PCA code? Just a sec. Just a sec. Let me just show you. Okay. Here we have the PC object and we are doing PCA.fit transform X standardized, right? This is X standardized. We have the new data X test standardized. We will simply give this data to PCA.fit transform. We will simply give this data to PCA.fit transform X test standardized, and whatever result this will give, we will simply utilize that. Okay. So the same object what we have created for training, we will be using the same object to transform the test data itself. Right? Understood? And this is not for PCA. This thing needs to be exactly same for every concept. If we did standard scaling, if we did standard scaling here, we did standardization. Where it was the standardization code. Here we did standardization. So we did fit transform on X. But when we will be having the X test, we will simply be using the same object SC, and we will simply be doing transform X test. Right? We should not retrain it for the X test data. We simply be doing sc.transform X test, not fit transform for the testing data. Here, number of components should be fixed. Exactly. It should be exactly fixed. Even we should not create a new PC object itself. The PC object what we have used in training, use the same object, just invoke the transform function and give the test data. Right? Perfect. And that's not only for PCA, we do it for every such transformations. For that also, label encoder, we created LE object, we did fit transform on train data, we will be doing transform only on test data. Clear? Yes guys, clear? Awesome. Perfect. Yes. Anyone, anything else, please? Yes guys, please. Anyone, anything else? Yeah, please. Sure, just a sec. Anurag, yeah. Yes.
Hey, Vilas. I'm
Yeah.
audible.
Yes, you're audible.
So I have a concern. Suppose we have a look at a model. Suppose we have a pricing we have received on a daily basis, but someday, like instances, we have missed the prices. So how can we get to know this is actual missing to predict from the previous experience? So in that case, how can we use which kind of model we can use?
Okay, so if I understood the problem correctly, let's say it's related to the time series data. We
Time
are
series or anything? Yeah.
okay. Anything. Let's take a time series as of now. This is a time we are calculating the daily sales or daily something
Yep.
y, and the trend is going on. The trend is going on. At certain point of time, we forgot,
Yeah. Correct.
right? And again we forgot, and
Correct.
that's how we have this thing. Okay, so in order to deal this, we have a logic called linear interpolation.
Okay.
Linear interpolation. So what it does, it creates a linear relationship kind of thing, and it fills these missing values as per that linear relationship. One method, okay, makes sense.
Yes.
Another method, moving average. So we can calculate the moving average with some good interval, whatever sounds good for a given data
And
set.
fill those values
Exactly,
where
as
yeah.
per the moving average.
Correct.
As
So
per the
actually,
moving average.
yeah, as per our concern which we have to see the not that much historical data. Just we have to see for the last 1 week, 2 week data. And if anything is missing, just indicate that it's a missing. Just highlight those things, not in the form like in raw data form.
We just need to highlight if it's missing,
Correct.
right?
Correct. We have to find those only the missing one
Okay,
on the
so
value. Yeah, on the
okay,
value
so
previous experience.
uh,
Just I explain you a little bit more. Suppose last week there is a data. Entire last week we have continuously received the prices, but in next week what happened? Monday we have received the prices, but Tuesday we haven't received.
okay,
Okay, so it's something sounds like there is a actual missing and there is some disturbance from the technology or any kind of issues will be there. So we are not sure. So they have to indicate and find this kind of issue over there.
so we just need to indicate that before Tuesday, on Monday itself, we need that indication that we are going to get missing. We are not going to get the data on Tuesday, something like that.
Correct. Currently, we are same thing we are doing on a SQL level, where we have like comparing the last 2 days data. But with the help of machine learning, where I wanted to look for the more than a week actually. So model will design in a such manner. Right now, we just checking the few of the spec and the value. Like if value is there in the previous and day previous, like today is suppose Wednesday. So they will go and have a look over the previous day data, and again the previous go will go and check the previous day data. Like two
If
days
it's
data they are
available or
checking.
not.
Yeah,
If it's
it's available.
available or not.
If it's continuously available, then if today is not missing, they will consider as a suspect. That way we have SQL, but we are looking for the machine learning model where we have implemented the same things but a huge parameter.
On a huge amount of data.
Correct.
Okay, suppose today is Tuesday. Okay, if I want to check for last 1 month, okay, today is 22nd February. I will go back and I will check till 22nd January. If I have all the records or if there is anything missing, that's what I'll check. Okay. Yes.
Yes. Correct.
Okay. Now, if there is something missing, now what we actually expect after this, the model should raise an alert or something. What should be the action in that case?
Yeah, model should raise an alert or just notify that for this date, this data is missing.
That's it, right?
Yes.
So we actually don't need machine learning for this. We can simply write a custom program. We can simply write a logic. We can simply write a program that can go back and check if the data is available or not. If the data is not available, it will simply drop an email or anything.
Yeah, that's fine. But problem is here, many of the data, like millions and billions of data there, they have continuously it's missing from the last many days. If you see, like from the 1 week, 2 weeks, like continuously last day there is no prices. This is a millions of data over here. So that's why we have encountered the challenges over here. So in that case, yeah. So challenges here we will receive the false suspect. We are looking for the true suspect over here. That's why we wanted to compare from the previous to
Okay,
previous date.
okay. So is it like we have a huge amount of factors,
Correct.
right? Let's say we have a lot of it's about the sales of the product. So let's say we have hundreds of products, something like that. We
Something
have
I just yeah, I can't say reveal the data, but I'm giving you the basic like reveal about that. Suppose it's a trading market, so there is a
Mhm.
bid and ask. Not every stock has a bid and ask. Only which have a liquidity. Many of them there is no buyer, no seller also. There might be a chances. Right?
Mhm.
So in such scenario, there is a false suspect. They don't have value from the long, like in many days. From the last 1 week, there is no any values. There is no buyer, no sellers kind of thing. But few
Okay.
of the contract or few of the uh, like sales, they having a continuously, sorry, everyone having an keenly looking for those stocks. And every day
Mhm.
we have the price for that. But in middle of something, there is no any price due to some technical anything, any issue might be the reason. So we are
Okay.
looking to find for those only.
Okay. On a real time itself, right?
Correct.
Like for current time period, if there is no buyer, nothing has been bidded.
But
Like
end of the day is also fine. It's not been an issue. If we are able to find at end of the day, if we are not able to work on the real time, end of the day is also fine for us.
okay, at the end of the day, if there is nothing, it should be raising a alert.
Yeah, alert or just notified us.
Okay, again, and this is something we have to do on lots of such factors.
Yeah, lots of data. Yeah.
Okay, okay. So the current problem is we get the alerts, but not for like what is the current problem here?
Currently, we are like as of now we are running it on, as I mentioned in the SQL basis. Right
Mhm.
now we are just in SQL, you know the limitation. We can't run it for the entire universe and whatever the factor we have. There is some limitations. We can't and running time is also more. So we are just looking for the other aspect we can like and we just increase our parameter too. Just right now, as I mentioned, you just we have a mentioning for the last 2 days only. If like last 2 days data, if value is there,
Mhm.
we if next day there is value is missing, we are as a created as a suspect. But with the help of machine learning, instead of 2 days, we wanted for the have a look for the last 3 4 days also.
Yeah, that's easy. See, okay, now how we can do it? We don't need any algorithm for this. Just read the data using read SQL or something. The database must be in some database server,
Yeah, yeah,
PSQL
yeah,
or somewhere, right?
yeah,
So you can use read SQL function to read the data, right?
yeah, yeah, yeah.
It will read on a real time. Let's say I right now I want to check for last 3 days. It
Correct.
will read the data. So I did the read CSV on df. So I'll simply do df dot ilock
Mhm.
minus 5 or okay minus 5 anything after minus 5 for all the columns. So what it will do? It will give me the recent 5 records. Okay.
Okay.
So I can save it in recent object recent equals to df dot ilock minus 5 colon everything after minus 5 and all the columns.
Mhm.
Now in recent I can check if there is anything missing. Recent where recent dot is null. It will simply return the values where we have the missing data. It will simply give all those records where we have missing. If there is anything we are getting here, we can simply raise the alert.
Yeah.
Easy?
So iloc minus 5 is indexing it, correct?
Yes.
Or so indexing for the column based. How can we take
No,
it for the
for the
last
next
5 days?
it's basically for the row based. So what I'm assuming the DF is like we have these are the different columns and these are the days.
Correct.
Okay, so when I did minus 5, it will simply give me the last 5 records like this.
So in that case, we have to run the query on the SQL for the last 5 days data, correct?
Not in SQL. We just read everything from the SQL and rest everything we can do in Python itself. We have read everything from the SQL. DF is having all the data. Minus 5 colon means last 5 records. It will like automatically fetch only last 5 records. and then we can check what all columns are missing, and we can raise according to that.
Okay, so it will like every day we have to run the same thing, like every day. So how can we do that? Like
We can simply write a while loop. We can simply write a while loop, and inside a while loop we can write this code and just add a sleep time of 25 hours. Sleep time of 24 hours, that is, it works in minutes, 60 minutes into 24 hours. Yeah, 16 to 24. Just add a sleep time of this. After every 24 hour, it will again check. It will read the data in real time, again check for the last 5. If there is anything missing, it will raise a concern.
okay, I will try it. Yes, thank you so much.
I can show you some sample codes.
Yeah, if you have
Just a sec. So some similar kind of thing is there. We are actually referring to a S3 bucket, and we are checking if there is anything new records inserted, like candidates are uploading their CVs and everything on the server. So here is a sleep time of 60 into 30, means it will check for 30 minutes. It is running after 30 minutes. It will check if there is anything new, it will parse and insert to the database. So this code is running inside a while loop. If I show you, this code is running inside a while loop. Yeah, here it is. While true, so it's running continuously. No one is going to stop this. It's like no one is going to stop or re-execute this code. We have put it on execution for once, and it is running for all time.
it's running on your internal server or like cloud based?
No, it's a server. It's a cloud server. It's a AWS instance, Windows instance. I think EC2 or something. It's a Windows instance in which we are running the script. We can run it at any server, like Linux or whatever we have. We can create a py file and we can run that there. So it will check after 30 minutes. It will recheck after 30 minutes. If there is any new candidate, it will work for that candidate. If there are bunch of new candidates, it will process all of them. So that's what I meant to say. Just create a while loop, implement the logic to detect the missing values and raise alert, and re-execute that logic for after 24 hours. Like you can just add a sleep time at the end of a while loop. So after 24 hours, it will recheck.
Yeah, I will ask. Thank you so much. Can you do one more thing over here? Can you one day, if you have a time, like not right now, one day, just you show us how can whatever the model you have designed over, and just how can we implement it? Like suppose you have
Deployment.
Deployment kind of
Yeah,
thing.
sure, definitely.
That will be very helpful for us actually. So how
Yes. That is something I've also planned. Like if we get time, we will definitely be talking about the deployment, Flask API. And if you go to the another directory what I have shared, another Google Drive, there we already have uploaded this deployment scripts. If I show you once again, this is the one. And FlaskML API, there is a file in which an API has been created for the deployment. Here it is, flaskmlapi.py.
Okay.
So you can also explore this one, and we will also talk about the deployment at the end.
Yeah, I have worked for the Streamlight long back. Streamlight is something. Yeah. Streamlight something. It's pretty easy one, straightforward.
Okay.
Flask one. Yeah, I have worked, but not in deep back.
These are the web frameworks only, how to interact with HTTP request and HTTP responses.
Yeah.
Yes. Perfect. So
yeah, thank you.
Yeah.
I will check and let you know.
Sure.
Class, yeah. Right. Okay, man. Thank you so much.
Perfect. So that's it. That's everything for the day, guys. Thank you, everyone. Thank you all. See you tomorrow.